So we are at the final video in the course Systems Biology, Digital Twins and AI. We have now learned basically everything in terms of methods and how to do things. And now we are just going to sort of enjoy the view and also zoom out a little bit in terms of understanding what's important to use these things in a sound way. What are the pitfalls that it's easy to fall in? What are the things that you should think about to not use these in an unsound way? So we have the digital twins in our hands, and now we want to use them in end usage in pharma and EHealth 3.0, which is the digital twin-based EHealth. So sound usage across applications throughout your lifespan, from going to school to concerts to hospital situations of various types, including drug development. Okay, so let's first start by looking at the FDA, the Food and Drug Administration in the US, and they have some criteria which basically specify when you can use a digital twin in end usage decisions, in particular when you want to approve a new drug or a new biomedical product. And then we'll hold that up, those criteria, which are very sound, I think, to some particular sort of points and contrast them to how modeling is done sometimes in other ways, which is less sound. So I'll point out particularly the importance of using data for validation. So not only use data for parameterization, but also for validation. And I will point out that there are many situations where the simulation of a model has a way too central place in modeling. It's, if you can do a simulation, you are done. It is often the case in many fields, and I really want to point out that this is not what the FDA says. This is not, if you want to use it for end usage, you need to go beyond that. And I also want to say that the validation becomes stronger the more qualitatively different it is compared to the training data. And this really points to the power of mechanistic models, which is, as you probably have noticed, is one thing I've tried to come back to many times in this course. And also the importance of knowing what is the uncertainty and what is the source of knowledge of a prediction. So if you have some kind of statement, we believe this will happen, we believe that you have a tumor, or that you should take this treatment, or whatever it is, then you want to know how certain are you, and what is the source of knowledge that you have for this. And those are really two important challenges of classical AI, non-hybrid AI, and machine learning. And that sort of is the basis for things like explainable AI, XAI, and physically inspired neural networks. But I want to contrast this a little bit to this type of hybrid models that we have here, which is a form of explainable AI and PINs, but it goes beyond that, I think. And then we are basically done. Then we'll sort of sum up and zoom out and look also beyond the course and beyond where we are now. Okay, let's jump in. So we have these FDA, Food and Drug Administration guidelines for usage of modeling in approval of biomedical engineering products and drugs. So it's a 5-step process where you first want to verify that you solve the underlying mathematical model correctly. For us, that's typically negligible. For the methods that and the models I talked about in this course, typically solving an ODE or even a DIE is quite straightforward. using a neural network or a trained machine learning model is also fairly straightforward. If you do partial differential equations, it's more of a challenge. If you go stochastic simulations, it might be more of a challenge. But for most of the examples that I talked about the most in the course, it's not a big issue. But what I did talk about a lot is how to use validation data, how to use data to check if the underlying mathematical model actually represents reality. And this is where we go beyond simulations, because you need to compare the simulations with new data that the model hasn't been trained to. Here we need experimental evidence. And then you need to quantify that uncertainty together with all of the other uncertainties that you have to have the uncertainty of the output. So a simulation with a prediction, a statement with an uncertainty, statement with an uncertainty. And this we talked about a lot, is core predictions and how to do practical observability analysis and so on. This was important in block 2. So this has been really a cornerstone of the course. And now if you really want to use this, then you also need to look at this validation evidence, the way that you validate the model. Does that really support using the model in the way that you want to use it, in the context that you want to use it? And based on that evidence, but also all of the other evidence that you have, is there any sort of belief in the predictive capability of the model for the context of use? So here it's much less of a sort of methods. Up here, this is how to simulate a model. This is just numerics. These things I went through in block 2, how to do this, and block 3 for nonlinear mixed effect models, and for machine learning in block 4. So that's methods. Here, this is much more of a judgment call. But that doesn't mean that it's less important. On the contrary, it's really important because this is when you make the final judgment call, if you can use the predictions or not. So to sort of bring this point home in the end here, so here you have some 2 parameters that describe different ways of using the model, and you might have validated the model here, so to say, in this operating range here. And then if you're sort of here, if this is where you want to use the model with the green area here, these 2 dots, then you should sort of be fine. But if you want to use it over here, then maybe you're a little bit outside of the validation domain. And if you are over here, then you're even maybe outside of where the model is even valid, because it's violating some fundamental assumptions in the model. So it's not like you validate the model and then it's true for any application. It really depends on the place that you want to use the model. Is that similar where you validated the model? So if we sort of should have that in this meal simulation, which I'll come back to a couple of times in the course, then here we have the glucose concentration in the blood. We have the data from the glucose sensor, and we have the simulation, and we train the model on the breakfast response. So this is what we use to parameterize the model and to make it into a digital twin and to train the parameters. That's the estimation data, the training data. Then the validation data would be the lunch response. Can we correctly predict just by knowing the input, which is what you ate for lunch and when and how long time it took to eat? Can you then correctly predict the lunch response? If you can, then you have done a validation. And then the question is, do you want to use it to simulate something very similar? For instance, like the dinner response, where you're just eating something quite similar to what you ate over lunch. Then you're probably fine because your context of use is similar to where you did your validation. But if you want to use it to validate or to say what will happen if I have a drug, and you have no data that's similar to that or what the drug is modifying in your system, then your validation is not at all good enough for the context of use. So you need to keep track of this sort of distance. So those are the FDA criteria. Those are really sound, I think, for checking vital things to check. So, and here you see that you also have an uncertainty of the prediction. Here it's symbolic, but you learned in the course how to actually calculate these uncertainties. So these are the FDA criteria. So now let's hold that up to some common ways of using modeling. And I want to sort of train you to have alarm bells going off in the back of your head if you see some of these examples. So a very common thing that you see in many conferences is that you have some kind of CT image or MR image for the heart. So you have different aspects of the heart. And then you might quantify these type of image to get a patient-specific anatomy and patient-specific parameters that go into the simulation of the model to specify the sort of the way the model is set up. And then you can do these beautiful advanced partial differential equation type of models or simulations. And in many cases, often when you see these type of things, that's all you see. You see these type of simulations, and they look very impressive, but they are never validated. The output of the model, the simulation output of the model is never compared with data. And it's not compared with data that it hasn't seen. So it's not enough to use the data to parameterize the model. You also need to use data. If you want to do a validation of the model, you also need to compare the simulated output with corresponding measurements for the same output in the same condition. And that's often not the case in this field. And in many other fields as well. One other field where this very rarely happens is in ecological network models. And both of these are used to make really important decisions about what happens in the body of a person or what happens when we do things in society to our ecological networks, how this affects how we implement laws and how we think about what we do to nature. So it's very important that you sort of coming with knowledge about modeling, that when you enter as citizen and you enter in the debate of this, or if you enter as a scientist or an engineer to improve things, that these are things that you really think about. If we should use models to make decisions, then we need to validate the models by looking at can the model predict data that we then collect after that. So you should always look to see if the model has been able to predict independent validation data that it hasn't been trained to. And the more different the validation data is compared to the training data, the more impressive it is. So in the example of just simulating a lunch response where you already trained the model to a breakfast response, that's not very impressive. But that you can do with sort of previous model and this Dalaman model that I talked about before. And basically what we have learned in this course is how to subdivide such a top-level model into a modular model where we have different organs that take up different parts of the glucose or secrete insulin. So these are the input-output profiles of these different modules. And we learn how to do this in a hierarchical way, how to also describe what happens inside cells. And in this particular paper that was published last year, then we did this to describe how amino acids and glucose crosstalk with each other inside the liver. And to train the data, we had some endogenous glucose production measurements from an MRI. We see how this goes down in response to a meal. Here you see the uncertainty of the simulations in the area with red here. Liver glycogen, which also can measure with an MRI. So this is estimation data used to train the model. And validation is used to so the model hasn't been trained on these data. It's been trained on these data. So this we formulated a cost function and optimized the cost function. to train on this data, but we didn't train it on this data. So this was just a validation. But you see, it's fairly similar. This is also endogenous glucose production, but it's in a slightly different patient group. Here it's healthy control, so it's type 2 diabetes patients. But what we looked for in this particular paper, and which I think you should always look for and do the best you can to really find something like this, is a fundamentally different type of prediction. So here you see you eat a meal and then you see what happens. Here we eat a meal before and after 48-hour fasting. And we eat a very particular type of meal, which only consists of proteins. And then we look at what is the response in plasma glucose. And here the model says that now, after 48-hour fasting, but not really earlier than that, then you would suddenly see an increase in the glucose level go up in the blood. So that's a fundamentally new type of prediction that is not there in any of the training data. So the model has not been trained on anything that's similar to that. But because the model describes the crosstalk between the glycogen and the endogenous glucose production, we know that if we haven't eaten for a long time, then the glycogen will be very low, meaning that the conversion of an amino acid to glucose will have been upregulated. And it will have been upregulated so much that even though you drink quite little protein here, you should see a response not only in sort of the usage inside the liver, but even that the liver has a surplus of glucose that it will send out to the other organs and to the plasma. And the uptake of the other organs will not be so fast that you don't see the increase. So you would see an increase that it goes up from around 3 to around 5, something like this, and then goes down after another 2 hours. So that was a qualitatively new prediction that was not there in any of the training data. And therefore, it was sort of really the model sticking out its neck. You have not seen this in any training data, but I believe something very new will happen. Therefore, we did the experiments after that. So we did the fasting for 48 hours, and we put on the glucose sensor to see that the data here, which are the different dots here, are really going up and then down in response to this protein tolerance test. We don't drink any glucose at all. We just drink proteins. But anyway, we see this increase and the decrease. So I think this is an example of a sort of qualitatively new prediction. And you should always look for that because those are the strongest ones. But then, of course, if you also want to use it to make decisions, you should also have a validation that's similar to what you want to use it for. Another comparison. So here we have the ChatGPT, which is very, very popular nowadays, but is the result of lots and lots of research over many years. Since there was this hype, I tested it out about a year ago when it came. And then I asked it, who was the prime minister in Sweden in 1980? And it says Olof Palme. And then it continued saying Olof Palme was the prime minister of Sweden between 69 and 76 and from 82 to 86. And then I responded, doesn't that mean that he was not the prime minister in 1980? And then the ChatGPT actually did realize that yes, this is a mistake. He was not the prime minister in 1980. Torbjörn Fälldin was the prime minister in 1980, which is correct. But this just shows that it can sort of here look very confident. This is a quite easy question, and it somehow did know in the sense that it knows anything, and we'll come back to that very soon. That it was Torbjörn Fälldin that was the correct answer. But still, the string that came out was something that was wrong. And there are many, many such examples. If you ask it to say something about a philosopher that doesn't exist, or about some references for something that also doesn't exist, it would just make up references. That seems plausible. That seems like, yeah, this could be true. but in reality, it's not. And this is because what this type of model is a black box model. It takes an input string, which is the question, and it generates an output string, which are these two responses. So that's the only thing it does. And it has forgotten all of the data that was used to train the network. It doesn't know things. It's just something that takes an input and then it generates an output. So the output here would be those last nodes in the neural network that we talked about in the first video in this blog. So that would be the string. It predicts basically the characters and the words, but it doesn't understand things. And the trained model doesn't know things. It just has an ability to predict what is a likely text. And even more, it doesn't know the source of evidence, therefore it doesn't know the uncertainty. It doesn't know that this is wrong. The first answer was wrong and the second one is right. It doesn't know that. It just generates an output. And this is, of course, very critical shortcomings at the moment that machine learning models need to get a grip of. And that it's important that you as a citizen, when you sort of discuss this type of thing, or you as an engineer, when you want to improve these type of things, you think about these shortcomings and you try to address them. And there is a whole direction of machine learning and AI that tries to get the grip of that, and that's called explainable AI. So if you have an image like this, and you want to determine if there is a tumor in this image or not, then there are many examples of publications in high-impact journals where you say that, oh, we can determine this with almost 100% accuracy. But then when you dig a little bit further and you do more cross-validation on independent data sets, you realize that maybe it was so that all of the tumor images was done on one scanner. And in the image is a meta tag, which is the name of the scanner. Then the only thing that the AI is using to calculate if there is a tumor or not is the name of the scanner. And then it's, of course, completely unable on a new data, which comes from a new scanner, to know if it is a tumor or not, because it hasn't learned how to look in the image in the right way. It only looks at the name of the scanner. It doesn't look at the image and tries to identify the tumor. So that's a common problem. So you really need to know what is it using as a basis for its decision to gain more confidence. So you want to have the explanation for why it's saying that there is a tumor. If it's saying, well, it's because the name of the scanner is this and this, then of course you know that you can't trust it at all. It is just bullshit. But if it tells you, well, actually in this area here of the image, it looks like there is some traces of something that is a little bit weird, then that is something that a radiologist or some other kind of doctor can look at and see, yeah, you're probably right. I think it seems like you're looking in the right place, and I think I tend to agree with you. Then it can sort of support the radiologist and maybe even do a pre-training and so on. And this then is part of the explanation that, okay, this is where I'm looking to make my decision. And this then can be done using a sensitivity analysis. So you remember this DY/DP that we had in block 1 and block 2. So there's the output. How is the output changing when you're changing a parameter? Here is how is the output changing when you're changing an input? So the input here is the image. If you change a part of the image here, would that change your decision? If that's true for sufficiently large perturbations, then this is an important part. But no matter what you change here, you will not change the decision. Then this is not an important part of the image, and so So by doing this sort of sensitivity analysis, how much is the decision impacted by changes in the input, you can get this type of more information explainable AI. Another thing that's sort of done in the machine learning community to bring more knowledge in to the situation is to use physics-informed neural networks. Then you might combine a neural network with some kind of partial differential equations, such as the Navier-Stokes equations for simulating blood flow, which provide additional knowledge and which is beneficiary, especially when you don't have enough training data to learn all of the information that's already embedded into the Navier-Stokes equation. So these type of neural networks are called pins. And some people think that they are a very good idea. Another approach, which is not based on neural networks necessarily, but maybe this type of arcs or regression models, is to use some kind of prior knowledge when you create the data. So if what you are looking for is a relationship between the voltage, the resistance, and the current, and you have data for all of those for some kind of device that you want to characterize somehow, then maybe instead of just sending in the voltage, the resistance, and the current, maybe you should also send in the resistance times the current as a new variable into the model. And the reason for that is that you know already from sort of first principles that the resistance times the current, or times I, is actually what is equal to U if you sort of have the normal equation, and then maybe you have some nonlinearities and you have some other things that makes this a little bit more complicated, but this is sort of the first approximation. So therefore, having a variable that is like this will probably greatly enhance your ability to predict the U here. So that's another way. So sort of you help the model by bringing some knowledge already into the formulation of the problem. And while these are sort of has some benefits, I think that what you have learned in this course, which is hybrid models, it does the same thing as these does, but you let each model deal with the data that is most suited to deal with. So if you come back to this image, which was the last one on the previous video, then basically the knowledge that you have, the mechanistic knowledge and the physics and the biochemistry and blood flow and so on, all of that goes into the mechanistic models. And then you have the sensor data and the time series and the electronic healthcare records and so on. That also goes into here. And then you have the images and the omics, which can go in both directions depending on how you want to look at them. And then you have the things that basically cannot go into the mechanistic model, but that can go into the machine learning model, which is things like sociodemographics and large clinical studies like UK Biobank and SCAPIS and so on. Those go into the machine learning models. And because we have this hybrid combination of these two, each data can go into where it's suited the best. So these pins, physically informed neural networks, or these other ways where you take the product of things, that's sort of to take a small fraction of the knowledge that you have, and then you try to put that into these models. Whereas a hybrid model, it sort of has both these models, and it tries to sort of really use the strength and use all of the power of all of the models and then bring them together. So you have something that goes beyond what any of the models can do individually. So for instance, you can simulate the risk, how that changes in different scenarios. You can't do that using the machine learning models, and you cannot do that using the mechanistic models. You can only do that using the hybrid combination. And that sort of brings us to the other end usage, which is e-health. And here I will only say very shortly that e-health exists in 3 generations, you could say. The The first is to communicate data and just conversations with each other, to basically go to the doctor online. This is something that's already exists, and that's sort of the first generation of EHealth. The second is the one that's maybe the most hype around now, which is to use AI and machine learning, but it's narrow AI, which is sort of specific to each use case. It's not general AI. So you don't use any mechanistic understanding, and it's hard to generalize and understand. And there's lots of data that you can't use if it's sort of low, if you don't have these thousands and thousands of training data. So therefore, the EHealth 3.0, where you have this hybrid M4 models and digital twins, which is what you learned in this course. There you can use all types of data and all types of knowledge, including new data that wasn't used to train the model, because it's extendable. And you can do these type of things like simulate how the risk and the is changing in scenarios, and you can get mechanistic insights and explanations basically for free. So this is sort of the general AI. It's much more flexible. You can use it for much more things than you originally intended. And if you want to learn more about this and work more on this, and you are still a student, you should look up the course TBMI 28 and the courses that prepares you for that. So it's part of there are some 3-4 courses that are in the series, and then you as engineers will collaborate with medical personnel like physiotherapists and so on, and nurses that will use the EHealth. So you will work together in cross-disciplinary teams. So this is not part of this course. This course is now essentially over. But if you want to continue, and if you want to use what you have learned here in this course, which is a fairly methodological course, if you want to use that in applied projects, then you should take one of these courses.